Welcome to CPE 350, Chapter 6, Section 6.1. We'll be starting example 11 in this video, looking at heat transfer in a fin and deriving the governing equation to describe this. Our problem is a heat source is isothermal at T base. From this heat source we have a fin used to cool it. The fin is rectangular with a very small dimension delta H, but a very long length and width. The fin radiates out into the air, which is isothermal at ambient temperature TA. And our job is to determine the temperature profile through this fin. So we start by drawing a differential shell element. We're going to consider unidirectional heat transfer in the x direction. So our shell is going to have a differential thickness delta x in that x direction. We're going to perform an energy balance over the shell using our standard methods. And we note that there's no generation within the fin. All of the generation is coming from something upstream of that base from which the fin is attached. Also, we're going to assume that this is a steady state problem, so there's no accumulation. Our first in and out terms are going to be somewhat familiar. It's just the heat flux in at x minus the heat flux out at x plus delta x multiplied by the area through which heat is transferring. And heat is transferring in the x direction, so the area it's transferring through is going to be in the yz plane, and that's W times h. That's the area of heat transfer. Our second term, our third term, is our convective term, and we're just using Newton's law of cooling here for a rectilinear geometry. We have our thermal transfer coefficient h, and we're going to multiply that by the area through which heat is convecting. This takes a little bit of explanation here. So the areas we're looking at are on the top and the bottom of the flat fin pieces, and that's in the yx plane. So we're looking at W delta x as our area, and there's one area on the top side of the fin and one area on the bottom side of the fin, so the total area is 2 times W delta x. Why do we not include those little tiny squares that are in the zx plane? The reason is yes, there is absolutely heat convecting from those tiny squares, but because the fin is considered to be very, very thin in the z direction, the area from which heat is lost on the sides of the fin, the thin sides, is negligible, and so we're just not going to calculate it because it would make our equation more difficult. And this is a good approximation, it works. And finally, our heat difference, our gradient, is going to be the temperature, which is going to be isothermal when the shell is infinitesimally small. So it's whatever temperature the shell is at, T, which varies, minus the ambient air, because it's always convecting from the fin into the ambient air. So that's our energy balance, and we're going to just divide both sides of the energy balance by W delta x to simplify it a little bit. When we do that, we've got something that starts to look like a derivative as the first term, and something that doesn't look like a derivative as the second term. We take the limit as delta x goes to 0. H is just a constant. The derivative is negative because we're looking at an x minus an x plus delta x, so that's the definition of a negative derivative. And our convective term remains unchanged. So our governing equation then, we can substitute in Fourier's law for a slab for Q sub x. And when we do that, we are able to write the expression entirely in terms of t and x variables. We assume that k is constant, divide both sides of the equation by h, and we get our governing differential equation. So in this equation, so we take our governing differential equation and we recognize that it's second order with respect to x, so we're going to need two boundary conditions. Our first boundary condition is pretty straightforward. We know that the base of the fin is the temperature of the base, which is TB, So that's t of x equal to 0 equals t base. That's called a Dirichlet boundary condition. Our second condition is going to be a little more difficult to understand. If we look at the geometry of the problem, we're considering unidirectional heat flux through the fin in the x direction. Yes, there's convection coming off the surface of the fin, which is not going to be in that x direction, but we've kind of pseudo unidirectionalized it by the way we've written Newton's law of cooling. So if we consider heat flux up to the end of the fin, there's this problem where the very tip of the fin, in red, is in air. So yes, there's obviously heat that's going to be convecting from that tip into the air, but it's going to be so much less heat transfer than all the other heat transfer in the x direction, because conduction is really, really fast. It transfers a lot of heat, and convection from that little tiny surface area is going to be very small. So we make an approximation and we say that the flux at the very tip of the fin is basically 0. And so once we write that out, it's an approximation. We can then plug in Fourier's law and say, well, negative k dt dx at x equal to L is going to be 0. And we can further simplify it by dividing by negative k. So we just get a flux boundary condition dt dx at L equals 0. And that's a Neumann boundary condition. And that's the second boundary condition we're going to need to solve this problem. Thanks for listening, and we'll non-dimensionalize this problem in the next video.